In this video, we're going to look at energy conservation. Now, what does it mean by energy conservation? Energy conservation is stating that energy cannot be created or destroyed. So energy doesn't just suddenly go poof. It's not a magician. Okay? It's always there, and it's always the same. Your total energy is always the same. This includes potential, kinetic, and any other form of energy, which we usually count as 0. So we figured out last time how to calculate total energy. Now we're going to say total energy, no matter where you are, is always going to be the same value. So up here you have a total energy of 50. As you slide down, your velocity goes up, so your kinetic energy goes up. Your potential energy goes down because you're sliding downwards, but they still add up to 50. So no matter where you are in the system, your total energy adds up to be the same thing. In this case, it's 50,000 joules. And the reason why this happens is because energy isn't created or destroyed, it doesn't suddenly go poof, but it's transferred between types. So kinetic energy becomes potential, and potential energy becomes kinetic. So as you start at the top of the hill and slide down, potential energy becomes kinetic. Your potential energy goes down, your kinetic energy goes up, potential became kinetic. When you reach this point here, you started traveling up. Well, as you started traveling up, your kinetic energy went down. You slow down as you go up, right? If you throw something in the air, it slows down. But its potential energy increases because it's going up. So kinetic became potential. So if you think about a ball being thrown in the air, it gains height, so it gains potential, but it loses speed, so it loses kinetic. So kinetic becomes potential. And if that same ball is being dropped, it gains speed as it goes down. So it gains potential, but it loses, it gains kinetic, but it loses potential because it loses height. So energy becomes transferred, not created or destroyed, just something else. Now let's break this down. If I told you that total energy remains constant, that means the energy in the first situation equals the energy in the second situation. Okay, so if I pick two things, the ball being thrown up, I pick when it leaves my hand to its maximum height. Two different spots. Any two spots in that travel of the ball is going to be the same. So I say, okay, let's say this is spot 1, this is spot 2. Those two have the same energy. Or initial energy equals final energy. You can also think about it that way. Wherever you start is the same as wherever you finish. Either one works. Okay? So, that's your total energy. Well, total energy equals Ke plus Pe plus Q. Kinetic plus potential plus internal energy. So you get this. Because that becomes this, and that becomes that. And they still equal, right? So we're just kind of expanding that total energy out. Now, if we consider Q to be 0, which we usually do, we get this. Now we expand it even more. From here to here, we said ET equals Ke plus Pe plus Q. From here to here, we just put in what kinetic energy equals and what potential energy equals. And we expand it out more, and we get this big equation. Now this big equation is nice and useful. This equation is particularly more useful, and let me show you why. Because it allows you to cancel something out. So take a second and see if you can't figure out what can always cancel when you expand it out like this. Well, hopefully you saw that mass is present in all of them. So you get an even simpler equation. 1/2 v initial squared plus g height initial equals 1/2 v final squared plus g h final. Alright, so if you're not given the mass, that's okay. You can still find out information. You can still use energy conservation. While if you stuck with this equation, you'd have to know the mass to be able to find your kinetic energy and your potential energy. So that extra step allows you to cancel mass out to make it not important. If you're given the mass, well, great. Don't even have to worry about making that step. You can stick with the other equation if you like it better. Okay? And now another thing, when you look at this equation, either one of these, know that oftentimes one of your things are 0. Let's say you started at rest, then your initial velocity is 0, so your initial kinetic energy is 0. Or you ended at the ground level, so your final potential is 0. Things like that. So keep in mind some of these things might be able to be crossed out even more. Alright, let's look at an example, because this is best understood with examples. Alright, 10-kilogram cart is at rest at the top of the highest hill. What is the velocity at point B? And what is the height it is traveling? So let's look at the velocity at point B. We're just going to do one part at a time. Alright, well, we're given the mass, which is cool. We can include that. So we can solve for kinetic energy and potential energy and all that. But I'm going to do it as if we didn't know the mass. If you knew the mass, you can just plug it in. It doesn't make it right. It doesn't make it wrong. It just makes it there. I'm going to cut it down. I'm going to say, well, I can cancel all my masses out, so that's exactly what I'm going to do. Because why deal with an extra number if you don't have to? Now we're looking at the velocity of B. So I'm going to say we're looking for our final velocity because we started at A and we ended at B. So we have 1/2 VI squared. VI is our initial velocity. Well, we started at rest, so VI is 0. At the top of the highest hill. Our highest point, HI, is 30 meters. And we ended at 10 meters. So there's all our variables we need to know because G is a constant. So we know 3 of the 4 variables, we're good to go. So we get 1/2 VI, which is 0. That cancels this out, right? Because 0 times 1/2 is 0, even if it is squared. Plus G, 9.81, times height, 30, equals 1/2. VF is what we don't know. Make sure you remember the square. Plus G, 9.81, times height is 10. Alright, all we got to do is undo what's being done. We have 9.81 times 30. So we got 294 equals 1/2 VF squared plus 98.1. So undo what's being done and you aim to please, if you remember that. So we're going to undo any kind of addition or subtraction. So subtract 98.1 from both sides. And we get 195.9 equals 1/2 V squared. Alright, so we got to undo what's being done, the multiplication. So we divide both sides by 1/2, multiply by 2, and we get 391.8 equals V squared. Take the square root, and you get 19.8 meters per second. Okay? That's total energy. Energy at one point, energy at the other. Now, if you'd used the mass, you could have solved for KE and PE at the top, and then set it equal to KE plus PE at the bottom, and done it that way, if you wanted to use the mass. And I'll tell you what, I'll solve it that way now. Note that I changed the final velocity to 3.267. 32.67 didn't actually make any sense, so that would have been an error, and it would have actually put us down even lower and below the ground. Alright, now I'm going to set it up as using the mass. So I'm not going to cancel the mass out. We're going to solve for the initial kinetic, the initial potential. Okay, we're not just solving for velocity or height, we're solving for the actual energy. Now, we're setting initial equal to final. Our initial point can be either A or B. It doesn't matter which one, because total energy is always the same. Final is going to be C, because we need to have C in there somewhere. Now, I'm going to pick my initial point as A. Why am I doing that? I'm doing that because initially our velocity is at rest, which means that our initial kinetic energy is 0, which makes less math for me to do. It's not wrong to pick B and use the velocity at B and the height at B. That will work out the same. But A is just so much easier because that initial kinetic energy, KE initial, equals 1/2 mv squared, which is 1/2 times 10 times 0 squared, which makes it 0. So initially, our kinetic energy is 0. Makes life easier that way. Now that initial potential energy, let's solve for that now. Our initial potential energy is mgh, which is 10 times 9.81 times the h, which is 30. So you end up with 10 times 9.81 times 30. And you get 2,943. Now that's going to equal our final kinetic energy. Our final kinetic energy is 1/2 mv squared again, which is 1/2 times mass, which is 10, times 3.267 squared. Now that squared is only for the 3.267, not for the 10 or the 0.5. So make sure when you plug it into your calculator you get 53.366, which I'm going to round to 53.4. Now we've got our final potential energy. Final potential, well, we're solving for that HF, so we're going to end up with PE equals mgh, which equals 10 times 9.81 times h. So it's 98.1 h. Alright, now all we have to do is solve for h. Undo what's being done to h, so we subtract 53.4 from both sides. So we get 2943 minus 53.4. You get 288.9.6 equals 98.1 h. Divide both sides by 98.1. And you get 29.455, which is 46 meters. And that's the height of the second hill. Alright, that's it for the lesson. Good luck on your homework.